I think my real interest, if I traced it back, was curiosity about the physical world, which is what physics is.
One might imagine, at least, that one's talking about nature when one's talking about the character of physical laws. But I don't want to talk about nature, but rather how we stand relative to nature now. I want to tell you what we think we know, and what there is to guess, and how one goes about guessing.
This is the piece of the equation which describes how the Higgs field acquires its value.
Welcome to our episode number 46 of our Physics Matter series. So our Physics Matter series, it promotes the global cooperation by introducing international organization and transferring knowledge on sustainable development and health. And it has been initiated as well by this inspiring light source, which is the SESAME. So we focus on scientific issues, so leveraging the research infrastructure like light source, neutron source, and particle accelerator, and many more exciting discoveries. So this popular science series aims to advance scientific knowledge across borders. For more than 3 years, our scientific expedition have gathered esteemed guest scientists and has provided a free access platform for everyone driven by scientific curiosity to engage also with experts. So my name is Christine Darve. I'm an engineering scientist at the European Spallation Source in Sweden. And we have with us, so Luisa Cifarelli from Bologna University, who is, like me, so the past chair of the Forum of International Physics, who is organizing so this series. So the visiting page that you can find, the page that you can see from the Forum of International Physics will open a lot of those presentation. You will find a lot of this material expedition that is enabled also to reach a larger audience. So please spread the word as well, so that we can hear more also about your own opinion, and maybe find the next year as well presentator. So today and the next month as well, so we are stepping in the world of healthcare and life science. So we recall that in September 2023, so we had already a colloquium by Professor Spencer from the NIH, so the National Institute of Health, so in the US, about the macromolecular mapping with magnetic resonance imaging. And in May 24, we had also for life science how in DSS, so neutron scattering is being used by exploring the cell membrane mechanism by Professor Giovanna Fragnetto, who is the science director here at DSS. So, but today, so we will discuss more possible therapy and also project that can be improving the quality of our life. So our special guest today is Dr. Sanja Damjanovic, who is a scientist for more than 20 years and has been working at prominent international research infrastructure and institutions such like CERN in Geneva, GSI, so the Helmoltz Center for Nuclear Research in Darmstadt in Germany. In addition as well to her scientific career, and this is a real added value, so she has been also honored of serving at as Minister of Science at the Government of Montenegro from November 2016 to December 2020. So she first graduated at the University of Belgrade, and she completed her PhD in Heidelberg, so in 2002. And in 2006, so she obtained at CERN the fellowship and award type position, becoming the first scientist from the former Yugoslavia, so directly employed by CERN, opening new gates. And this is why in 2007 as well, so she initiated an international cooperation agreement between Montenegro and CERN. So in and during her ministerial term, so she focused on developing Montenegro's innovation ecosystem and led the country to become the first outside of the European Union to adopt the smart specialization strategy, so which was approved by the European Commission in 2019. And her term ended so with this best grade for the chapter 25 of the 2020 European Commission report for the Montenegro. So Dr. Damjanovic also has promoted regional cooperation, leading the creation of the Southern European International Institute for Sustainable Technology. So now you know what SEEIST means. So we had a little quiz last time. So not sure that it was an easy way to remember, but it's really good to have Southeast Europe as well being represented. So she was the first chairperson of the SEEIST steering committee, and she's coordinated the SEEIST, so at the F3 roadmap in 2021 for that application. So after ministerial term, so she resumed her permanent position at GSI for the FAIR and continued to promote the SEEIST project. So she is the president of the General Assembly of the European Union 2020 History Plus project. So we'll hear a bit more. So which attracted more than 18 European research centers and clinics to finalize so the design phase for the SEEIST. She's also a member of the European Union Science Diplomacy Working Group at the International Academy of Science and Art in Bosnia and Herzegovina. So I think it's really a wonderful CV. And I would like also to take this opportunity so to send my best regards as well, our best regards to Professor Erwin Schopper, so 100 years old, but also the former director at CERN and one of the founding fathers of the SESAME, so that we represent here, and a strong supporter of the SEEIST. And also to Professor Ada Yona, who received her Nobel Prize in 2009 for chemistry, who was also, if you navigate so from our webpage, referring to this May 2024, you can see her presentation, and she's also directly involved with all this life science aspect. So now, Sanja, so you have roughly 45 minutes so where you can discuss so this subject, and we can also prepare the question in the question and answer box so that everyone have there, and we can share also the microphone at the end of the presentation so that you can ask live so your question. So with this short introduction, so then the screen is yours.
Yeah, thank you very much, Christina, for this nice introduction. So I will now start to share my screen. I hope you see my slides. So good afternoon or good morning to everyone. And dear Christina, thank you very much for this opportunity to present the special SEEIST project, as you explained, acronym for Southeast European International Institute for Sustainable Technologies, which has many missions, including beating cancer while shaping science in Southeast Europe, and all that under global mission of science diplomacy. Global research projects show what mankind is able to achieve when working together towards common goal. CERN in Geneva is actually the key example of a power of science diplomacy, and best definition for science or diplomacy is science done by many nations. In this picture, sorry, I have some problem in moving the slides. Okay, in this picture here, you see a Large Hadron Collider, which is the largest scientific instrument ever built, symbolizing global cooperation. Research infrastructures have already been proven to have a powerful social economic impact as a multinational venture, helping solving global challenges. Practically every research infrastructure is connected to some of global challenges. After CERN in Geneva and SESAME in the Middle East, SEEIST is yet another concrete example of science diplomacy. So inspired by these two projects, the states in Southeast Europe are joining forces to establish a large-scale competitive research infrastructures. And there are 10 potential members of SEEIST, countries which are marked in this picture here with the blue circles. So we are talking about this part of Europe, And you see here a large gray area, and these are 6 Western Balkan countries which are not yet part of European Union. So how it started? Official launch was in March 2017, when the government of Montenegro initiated SEEIST. Background: after 20 years working at CERN, I became Minister of Science of Montenegro at the end of 2016, as already mentioned by Christina. So it took me just 3 months to convince the government of Montenegro to initiate that project, and I was appointed as a political lead to set up SEEIST scientific framework. But what was the drive? As I mentioned at the beginning, SEEIST has many missions, including to promote collaboration between science, technology, and industry for regional advancement. It has a very important mission to revive a technological tradition which this region had in the past. I just want to remind you that, for example, ex-Yugoslavia was one of the founding members of CERN in 1954, when Austria, for example, was not. Or in this region, we had 3 large-scale research infrastructure based on new technology at that time, built before CERN in 1949, 50, and 51, and even we have Nobel Prize people from this region. However, due to recent histories, war in 1990s, that tradition unfortunately was completely interrupted. And since then, this region is strongly losing talents. And recently, I read an article from Al Jazeera pointing out that Western Balkan region per year is losing 3 billion euro based on outflow of people. So therefore, an important mission of the SEEIST project is to slow down or even to revert brain drain. Another important mission is to foster regional cooperation to mitigate, unfortunately, still existing tension between the countries in the region, to interrupt 70 years period without building any new large-scale research infrastructure based on new technologies, to utilize effectively EU cohesion funds and the global gateway through the economic investment plan for the Western Balkan. So it is obvious that this goal can only be achieved through a pan-European large-scale research infrastructure grounded in the latest technologies. So multidimensional aspects of SEEIST were quickly recognized by European Commission, leading it to the first financial support in 2019. I will show that later. A European Commissioner at that time, Carlos Moedas, was a strong advocate for SEEIST. And this slide here, I show you 3 Science Business articles highlighting the significance and potential impact of SEEIST. However, the question arose, what should SEEIST be to have a direct impact on society and also to easily attract political support? So the proposal for SEEIST to be an accelerator-based research infrastructure for cancer therapy and biomedical research with ion beams came early 2017, even before Montenegro initiated the project. It's already in January, February 2017, from 2 key pioneers in the use of ion beams to treat cancer. From Professor Hans Specht, who was pioneer of ultra-relativistic heavy ion physics at CERN. In 1980s, actually, Hans was the first spokesperson of a first heavy ion experiment at CERN. But he was also pioneer of ion cancer therapy as scientific director of GSI Helmholtz Center for Heavy Ion Research in Darmstadt, Germany. Although this topic was controversially discussed at that moment among the scientists, he strongly believed in it, he pushed it, and led the establishment of a pilot project at GSI, where the first 450 patients in Europe were treated with ion beams during the period 1997 to 2008. Hans was also played instrumental role in establishing the first hadron cancer therapy clinic in Europe, HIT in Heidelberg. And from Professor Ugo Amaldi at CERN, who is another pioneer in design of particle accelerator for cancer treatment and who was instrumental in establishing the second hadron cancer therapy in Europe, CNAO in Pavia in Italy. And Ugo was editor of the concept study and pre-TDR for SEEIST. So the pilot project using carbon ions was established at GSI, and the first patient in Europe treated with ion beams in 1997 was not treated in a clinic, but was treated at the GSI Accelerator facility. So this pilot project was set up during the period 93 to 97, and in just 4 years, in this short period, a lot of novel technologies were developed, including raster scan with intensity modulation. I will show what this what this brought to the future patient treatment. Then very complex and precise treatment plan. First, in situ PET monitoring for heavy ions, fast and safe beam control system, hospital-like cave and control room. And what was also nice was that during the treatment of the patient, the beam, there was a parallel beam provided also to researchers. And during that period, 97 to 2008, about 450 patients were treated, mostly who had cancer, skull-based cancer, chordoma and chondrosarcoma, but also prostate and other type of tumors. In 1998, this therapy project at GSI was inaugurated with the presence of German ministers at that time. And it was incredible that in the same event in 1998, official project proposal for the first ion clinic in Europe, Heidelberg clinic was presented and handed to the German government. So a spectacular success of treatment of this patient opened the way to the first ion clinic in Europe, a spin-off of GSI, Heidelberg Ion Therapy Facility. So you can see here a synchrotron transfer beam line. You have 2 patient rooms and a room for experiment. But what you see in this picture here, you have this gigantic blue structure. And this is the first heavy ion gantry, which was actually developed also thanks to the GSI accelerator people and magnet group. And these are actually 600 tons of magnets, which can steer the beam from such that the beam can enter the body of the patient from any direction. So HIT was the word, first heavy ion treatment facility with 360 rotating beam delivery, which is very important for optimal cancer treatment. So operation started in 2009. Up to now, 10,000 patients were treated, and it reached the goal of treating 1,000 patients per year. It specializes in treating many types of tumor. I will show you this list later. But now, after 15 years of running, it proves effectiveness and high survival rate of ion therapy beams, heavy ion beams. So in this next slide, you see particle therapy centers worldwide, and the orange points are much smaller proton therapies, while there are only 15 carbon ion therapies in the world, 4 in Europe, 7 in Japan, 2 in China, 1 in Taiwan, and up to now, about 57,000 patients were treated with ion beams, and about 350,000 patients were treated with protons. Now, the selection of accelerator-based research infrastructure for cancer therapy, biomedical research with ion beams as a core of SEEIST has boosted momentum, attracting both political support from 10 C countries and support from the broad Europe research community. So first political milestones, SEEIST became regional project. It's not anymore Montenegro project, but a regional project. So as Minister of Science, I serve as a science diplomacy missionary, visited all C countries individually, securing their support for the initiative, which was not so straightforward, given, as I mentioned before, still existing tension in the region. But then miracle happened. Only a few months after Montenegro initiated the project, declaration of intent was signed on the CERN ground in October, and that was a unique event at CERN. At CERN, every day you have a politician coming to visit CERN, but it was unique that at the same time we had 10 ministers at CERN, 8 countries signed declaration of intent, and 2 took observer status. And in 2019, there was another milestone, political milestone, memorandum of cooperation was signed by 6 prime ministers at the 6th summit of the Berlin process in 2019 in Poznań, Poland. In January 2018, the first intergovernmental steering committee was formed. I was elected to be the first chair. So, but very important, we reach scientific milestones. SEEIST attracted support from the broader European research community, and key for attraction was the unique comprehensive dimension of SEEIST, different from these 15 existing carbon ion centers. SEEIST is going to be unique in the sense that it will be both cancer therapy and research center, and 50% of the time, of daily beam time, will be dedicated to research. 2 strategic objectives, important strategic objectives are in this one initiative: fighting against cancer by developing the next generation of medical accelerators, explore new technologies by leveraging the experience gained from the construction of LHC, and building international cooperation while at the same time building scientific capacity in Southeast Europe. So SEEIST is going to offer multidimensional research. All this research are performed elsewhere, but SEEIST is going to be unique because all this research are going to be done in one site. And this includes preclinical, medical medical physics, radiobiology, ultra-high dose rate, flash therapy, which is today the hottest research topic in oncology, clinical, including clinical trials, material research, including testing radiation hardness of space microelectronics and shielding material. And cutting-edge, innovative and novel research in any of these topics will be possible thanks to breakthrough technology, which is currently being developing, which includes leading-edge multi-turn injection and multi-ion source system, meaning that at SEEIST we are going to use many large spectrum of testing, large spectrum of different ions beyond presently used protons and carbons. It will provide higher beam intensity, 10 times higher than currently achieved. Upgraded injector is going to be developed, multiple dose delivery modalities, which is very important, which will enable actually to use flash treatment techniques. And designing completely new fully superconducting machine, including superconducting gantry and superconducting synchrotron. So with a strong supporting consortium of 18 European research centers and clinics, including CERN and GSI, SEEIST is currently driving innovation in medical accelerators and treatment techniques through international collaboration. Another important political milestone was support by the European Commission. I mentioned you before that very quickly DGRTD recognized the importance of SEEIST, and they provided the first 1.5 million euro to start the first stage of the design phase, which is the second developing phase of the research infrastructure. And then additional 5 million we received via competitive EU Horizon at that time 2020 called HITRI Plus to finalize design study. Another important milestone was that SEEIST is recognized as one of the 6 leading EU Western Balkan projects in research innovation in the innovation agenda for the Western Balkan. And within DG NEAR, SEEIST became part of the economic investment plan for the Western Balkans, which this plan is part of a much larger initiative, Global Gateway. And in this text, the SEEIST is the only medical and research infrastructure. 9 billion euro is appointed for the Western Balkan by this economic investment plan for the period 21-27, with the goal to extend to 30 billion by 2030. So cancer is the second leading cause of death globally and was responsible for 10 million deaths in 2020. Globally, nearly 1 in 6 deaths is due to cancer. Each year, unfortunately, 400,000 children develop cancer. Cancer research is declared by the European Commission as one of the 5 missions, which is new instrument in the EU Horizon Europe program, but presently is entirely absent from the European research infrastructure landscape. And SEEIST actually has a goal to address this notable gap in this European research infrastructure landscape. But why heavy charged particles are superior to any other radiation in tumor therapy? So in this picture here, you see those deposited along the tissue depth, along the depth in the body. And the tumor region in this picture is indicated by a red arrow. So it is somewhere 15 centimeters inside the body. So conventional radiations, photons, this dark blue, and electrons, black line, have the property that the largest dose is deposited at the entrance to the body, and then smoothly is going down until it exits the body. But what you can see here is that the largest dose is deposited on the healthy cells, while only little dose is deposited on the tumor region. And then you need to repeat that many times. So different from conventional radiation, heavy charged particles have beautiful properties. When they enter the body, there is hardly any deposition of energy. So you can see this flat plateau. And all of a sudden, the whole dose is deposited at one point. And by adjusting the energy, you can be sure that you can do everything that this dose is actually deposited in the tumor region. So different from X-rays and electrons, heavy charged particles exhibit minimal lateral and angular scattering. These particles travel in virtually straight lines and stop at a specific penetration depth, delivering a high dose precisely at the end of ion path. And so this peak is actually called Bragg peak. And by changing the energy, you change this Bragg peak. And as mentioned just before, you can adjust energy that the optimum dose of heavy ions can be precisely localized at the tumor inside the patient while protecting surrounding healthy cells practically fully. And what is also nice that with this radiation, you can reach tumor wherever it is in the body. Now, carbon ions are more powerful. Carbon ions, which is shown here is a red line, are much more powerful than protons, shown here in green line, because they have much larger effective dose, because the dose is proportional to Z square. And actually, carbon ions and other heavy charged particles are the only instrument to treat so-called radioresistant tumors. And in general, this type of radiation is only possibility to treat tumors which are close to risk organ. For example, this is the only radiation with which you can treat pregnant women. So ion beams can scan tumor volume of any shape in lines in the same way electrons do in the television tube. And precise three-dimensional radiation is described in this picture here. So the depth in the volume of the tumor, this third dimension, is controlled by energy. By changing the energy, you change the Bragg peak along the depth. However, for the fixed depth, for the fixed energy, or for the fixed iso energy slice, you irradiate the tumor volume in the plane thanks to the two magnets which steer the beam in horizontal and vertical direction. And this is called raster technique, which I mentioned before, which was developed at GSI during this period 93 to 97, and which allows any shape of tumor to be irradiated with a precision of 1 millimeter. And three-dimensional imaging of the irradiated tumor volume is also done with millimeter accuracy, aligning with the precision of the treatment method. So here is just a small video which just describes what I said. So the depth energy slides, you change by changing the energy of the beam, and then for each fixed plane, you can see you have like pencil beam, which with two magnets, you can just irradiate only the tumor region. So the next slide shows that carbon ion therapy has real high effectiveness and survival probability. On the left picture, you see the probability that patients survive after 5 years of treatment, and in this particular case for the type of skull-based tumor chordomas. So what picture shows you that the survival probability by using carbon ions is about 90%, 60% by using protons, while only 10-20% if you use conventional radiation. On the right figure, you see effectiveness of carbon ion therapy. Here is an example for another tumor type, salivary gland tumor. And you see the first picture, pre-treatment situation with a large tumor in the brain. And then in the middle picture, treatment planning with carbon ions, and 6 weeks after the tumor is fully removed. And here is results of the survival probability, which is about 80% with carbon ions compared to 20% with conventional radiation. And also results shows that for patients below 45, age 45, it goes really to nearly 100%. So next slide shows the type of cancer which you can treat with ions. On the left, with cancer types which you can treat with carbon, and on the right, cancer types which you can treat with protons. Practically, they are the same type. And what you can see here is that you can treat prostate, liver, lung, central nervous system cancer, head and neck, eye, lymphomas, breast, and other type of tumors. And the next slide actually gives you precise list of all type of tumor which you can treat. And on the left, you can see indication for this type of tumors, which are now used for treating children. So hadron therapy is the most powerful, yet still a niche in cancer therapy. So main factors for limiting growing, cost, and size. So if you want for conventional radiation, you need to invest only 2 million. But if you want to have very effective, high survival probability rate therapy, you need to invest 250 million euros. And for example, here, one example in 2080, 22,000 patients were treated with hadron therapy, protons and carbons together. In contrast, 25 million patients were treated with conventional radiation. But this is actually now the opportunity to develop next generation ion therapy facility and to expand access to ion therapy for a much larger number of patients. Unfortunately, we know the distribution of GDP in the world is not homogeneous, and all that by leveraging collaboration to advance accelerator technologies and new treatment techniques, including developing more compact and cost-effective accelerator, incorporating R&D innovation for treatment like flash therapy. So 18 European research centers, I always mention 18, but now you will see which research centers are these, and clinics across 14 European countries are currently leading the development of these breakthrough in technologies. And SEEIST actually became a catalyst of that. It's also a strategic partner and potential reference user. So among these 18 research centers are CERN, GSI, all 4 currently existing ion clinics in Europe. And for the first time, by the way, they are working together, and other universities and research centers. So at CERN, a special study group was set. It's called Next Ion Medical Machine Study. And this group, together with a large number of international partners, are currently developing new generation of accelerator for cancer therapy. And they are currently working on 3 different types of designs. Improve a synchrotron, still warm, but with all this improvement which I mentioned before, which would also allow, will allow accelerator to be used for flash therapy treatment, then completely superconducting machine. And then you can see immediately here that the size of that machine is much smaller compared to the warm synchrotron, and consequently the price is much lower. Or a completely linear accelerator, and this is very fancy with high pulse frequency. GSI, biophysics, strong biophysics group is GSI, along international partners are advancing innovative flash radiotherapy, which is a novel approach using ultra-high dose rate. This flash therapy with heavy ions has potential to become a real powerful weapon in the fight against cancer, killing tumor in less than 1 second, but also reducing strongly toxicity, meaning reducing probability for metastasis. And with flash therapy, these are pulses of ultra-high radiation dose, and this dose is delivered with a very short time. The dose rate is larger, actually, or larger than 40 grays per second, and delivery time is less than 200 milliseconds. And for comparison, conventional radiation has dose rate of 1 gray per minute. So in this here, two picture on the left, you see that flash therapy was the cover page of Nature Review Clinical Oncology. And on the right side, it's interesting, ASTRO meeting, American Society Radiation Oncology meeting in 2018. There was a survey provided, what are the most important research in oncology? And in 2018, there was no flash. But in 2019, you can see that flash became really hottest topic, number one in the radiation oncology. So I show you the timeline of the SEEIST project. The project finished the first developing phase concept study. It's now finalizing the second developing phase, the design study. It's ready to start the preparatory phase, and with the new medical accelerator technology, it's possibility that the construction could start already end of next year. And if everything goes as planned, then the first patient could be treated in 2030, hopefully with this flash therapy. So, and now this is practically my last slide. Recently, EU Parliament approved 6 billion euros for a new growth plan for the Western Balkans, 2 billion grants and 4 billion loans. And it's very nice that a few Western Balkan countries in their reform agenda, which are connected to new growth plan, have SEEIST in. And SEEIST has a real potential to become a flagship project for EU enlargement. But I have another one more slide. I just want to say that this presentation is dedicated to the memory of Professor Hans Specht, who was, as I mentioned, pioneer in ultra-relativistic heavy ion physics and pioneer in hadron cancer therapy, but his rare combination of scientific excellence and strong management, along with his ability to make a brave decision, has left a lasting impact on society. Just want to mention that before the first patient was treated at GSI, at that time, technical director resigned. He could not take responsibility, and it was Hans, as the scientific director, who took that responsibility. And he was a strong advocate for international cooperation and played a crucial role for development and success of SEEIST. So thank you very much for your attention. I see that I did not exceed the time which I had. Thank you.
Thank you very much for this wonderful course information. We have seen in so many ways, so how we can and how science can contribute as well for all of that. And indeed, it's really nice to have given as well this this course. I mean, looking at the memory as well for Hans Specht. So thanks a lot. And also Ugo Amaldi, as you said, so who just turned 90 years old. So I think we can dedicate as well all this those pioneers who have been changing our life and improving it. So thank you very much. Should we have so questions from the audience, so we can take them now or later? You can raise your hand as well. We see that we have a question. Voilà, very good, from Yassir El Ghazi. So thanking you. And then, so for this valuable presentation, in one of your slides, so you mentioned a technique called the flash. That's where I wanted to come back at. Good. So which is this flash therapy. So as a PhD researcher interested in flash therapy, so I would like to know if there are any opportunities for collaboration, such as international, I mean, internship or those different type of conducting measurement related to the flash therapy technique?
So should I answer immediately? I think there is a great possibility here at GSI because GSI has a very strong biophysics group and they are making a lot of experiments. And if you visit GSI website, you will find that. And the director of biophysics group is great scientist, Marco Durante. They are participating in many EU projects and permanently they have positions and they very often advertise this position and they are going into two fields. They are interested in cancer therapy, but also space research because I think it's plenty of possibility for young people. And just please visit GSI website or you can contact me. I put you in contact with Marco Durante.
So thanks a lot. So that's really interesting as well to gather all the capacity as well, maybe as well from CERN or from other institutes in Europe. So now we have two questions that are being prepared. So by Kenzie Campbell. So I will just let you the possibility to write them unless you want to ask them directly. And this we can do too. Voilà. So the first one is, so is there any interface with the International Atomic Energy?
Okay, yes. For, yes, in the first financial support for SEEIST came actually from Atomic Energy Agency for capacity building. We got 5 million, not 5 million, sorry, €500,000 for capacity building. Yes, this is Atomic Energy Agency is now also involved in SEEIST. There will be a workshop organized in Greece in October. And what they are helping us with dissemination of this technique, building capacity in Southeast Europe, organizing workshop, spreading this information. So we have a close connection with the International Atomic Energy Agency.
Very good. So the second question, I think so, Daka will write it down as well. But in the meantime, so we have another question. So what is the current status of the SEEIST project? So do you have any decision about the country and that will host the infrastructure?
That is part of the preparatory phase because the first phase was a concept study, design phase is finalizing, and now that SEEIST is entering preparatory phase. Preparatory phase means location, long-term legal entity, and we are hopefully going again to apply for S3 roadmap 2026, and this time hopefully we are going to be successful. And then if we manage to be part of S3 2026 roadmap, then SEEIST will receive €4 million to work on all these aspects.
So that's a very precise roadmap. So what would happen also looking at the situation, so in also the Middle East, do you see like some kind of potential also contingency or stage approach or any kind of change? Or it's really written with the S3 as one of the things you mentioned?
For people who are from C countries, they can follow, and the Atomic Energy Agency, because we received this €500,000, is now organizing workshops and for example, there was recently organized visit of one of the ion therapy CNAO in Pavia. So if for people of C, from the C region, from these 10 countries which I mentioned, they can get support from Atomic Energy Agency directly to participate in many events.
Very good. Then the second question, so for Corey, so who is asking about any advice for young people interested in getting into the career in science diplomacy. So that was the other part.
In science diplomacy. I don't know, when I talk about science diplomacy, I always thinking about science done by many nations. I like these international research infrastructures. I think this is probably the best way where you can really learn about the power of science and science diplomacy. So, for example, if I was not a minister at the same time and scientists who work at CERN, it would be impossible to move such projects. So if you really work in international organization, you really learn a lot. My recommendation is go for international research organization. This is somehow which organization in infrastructures.
But I think what is important as well is like you to first being a talented scientist, and then to come into diplomacy. So this
research infrastructure, you grow up and you learn, you really learn, because you see this project, SEEIST, would not work without strong support of European research community. And this is exactly, for example, I did not mention, but SEEIST boosted another SEEIST in Europe. Now we have three Scandinavian countries working together to establish another SEEIST. This is Estonia, Latvia, and Lithuania. And the boost comes also from scientists from CERN. And so it's, I mean, this international cooperation is the key.
Yeah, it's essential. And as well, from this example, I think it was a really good one that you mentioned also with the NIMS. So that is also with countries that have been identified as well with this capacity from the university as well, or the capacity as well to be able to develop that.
Yes.
Very good. So we have another question. So from, and maybe there as well, I would mention the IUPAC potentially, because I know that they do a lot looking at indeed science diplomacy to be engaged in all those different global organizations. So I think it's also an important part to be engaged, to be proactive. That's really the important aspect. So just to answer also Nuri's second question. So then we have a question who is anonymous, but then it's to try to understand where the different funding, where the different countries in the Southeast Europe who have already contributed. So do we know distribution, order of magnitude?
So at this moment, the largest contribution came actually from Montenegro, but the goal for this project, the goal is to use EU structural funds, or for countries like Western Balkan, which are not member of EU, to use so-called IPA, Instrument for Pre-Accession Funds. And therefore, it's very important. There was a similar project we realized, it's called ELI, Extreme Light Infrastructure. And that in that project, 3 countries were involved: Hungary, Romania, and Czech Republic. And the project cost 850 million, while 700 million came from structural funds. So you see, this region is, we know, economically poor. It needs support. There is support because, as I mentioned, economic investment plan comes with the money, but in order to use that money, you need to have a pan-European dimension of the project. So the goal is to really boost as much as possible EU funds, at least 50% of EU funds, and the other contribution, largest contribution, will come from the country where the project is going to be located. But what is really nice about SEEIST, because every research infrastructure has a problem on sustainability. In this case, we don't have that problem. Why? Because 50% of the time is clinic. And our capacity is to treat 500 patients. And our SEEIST is going to be like medical CERN. So each country will have its own quota for patients. And each country will have their own medical doctor on the site. And because we want to have patients speaking the same language with a medical doctor. So by treating the patients, we will cover the largest part of operational costs, which is very nice. And then it will be self-running because, as I mentioned, every member of CERN will have its own quota of the patient. And that will contribute to the running of the project.
Which is the core running of the project. So this in situ aspect, so
yes,
essential, so for this sustainable way as well. So really good. So we have another question from Sirius Water, who is also the president of the International Association for Physics Students. So he's also with us in the organizing committee for the outreach and communication at the FIP. And he's asking as well, looking at your work, so in the country in Southeast Europe, so which is really important. So how do you think that this work impacted the community of young scientists in Southeast Europe? And what would be their view? Did you make any interview, or do you know what is the research and the career path that they are planning? How much impact does it have on the student?
Actually, the goal is actually that the future, that the SEEIST in the future will be operated by young people. And as I mentioned, the goal is to start to slow down brain drain because we permanently lose the people. And at some point, there was a question, but do you really have capacity to run the project? I can tell you that at CERN, on the CERN ground, you have 200 young people from the CE region working, and they are very much positive to go back to their country in case the country offer high-tech technology. So when we presented the first phase concept study, we organized a forum in Trieste in ICTP Institute. And you will not believe, among the potential user community or scientists, we had half people from diaspora and half from inside the countries. So, I mean, I myself, I'm not young anymore, unfortunately, but if SEEIST would exist in one of these C countries, I would be willing to run there and work there. I think this will be a magnet. This will be obvious magnet for young people.
To attract the young people, indeed.
Yes.
And one important aspect is this, the existing capacity as well from the industry point of view. You were speaking about this high tech. When you speak about the flash,
yes.
A bit, we need to make sure as well that the industry and the operation of all those institutes as well can be sustainable. So that's would depend as well on this kind of map that the country has from the industrial point of view.
Right. It is. Thanks for pointing that, Christina, because as I mentioned, the cost of this SEEIST project is 250 million euro, and about 190 are high-tech components and 60 other building, etc. But the 250 million is going to industry. And so with SEEIST, what we are going to do, we want to empower European industry, but at the same time to try to build, to increase capacity of industries, local industries, because all components are not only high-tech, but even from this region, in particular Slovenia, there are very famous companies like Cozy Lab, which are making control system for practically all research infrastructure within the region. So it exists, and this will be also catalyst to empower industry.
And I think it's a key, indeed, to empower the industry, existing one, and potentially as well, it's a niche, as you said, for new technology and new development. So again, this ecosystem between the industry, but together with the environment and research infrastructure, developing with brighter new early career scientists and students that are listening to us now. So maybe while waiting, if there are other questions. So what about, because you were showing also a map where looking at Africa, I mean, there is looking at the therapy, I mean, it's empty. So if we were looking at a way to model or to try to clone, I mean, those equipment or maybe part of the equipment, what would you advise as well? How would it be maybe a way forward, a roadmap for supporting Africa? And that could lead to next month as well. So I see that we have in the audience, so also the next speaker, if she can potentially speak, so Menji Durason. So what do you advise as well? Lesson learned, social, economical, and then plan ahead.
For cancer therapy.
In less developed country.
Yes, exactly. So I think if budget is here, that's very nice. But unfortunately, as I said, if you look at GDP distribution in the world, it's not homogeneous. But if you see that a part of the world where GDP is low, you can see that probability for cancer is much higher and mortality is much higher. So I think in abstract, which I wrote, I mentioned that we really need to do everything to use more science for society, in particular for health, and that we need to use more like this beauty of Bragg Peak to save the life of people. So you know, in my opinion, this instrument is so important and so strong that everybody should do something to empower the health of the people.
Indeed, and to train the doctor. So this is so wonderful. So we just get the green light for Manji, who is able to speak. So I just allow her to talk right now. So welcome with us, so Manji. It did give us your side as well, how and why. Maybe also with this African School of Physics, we can mention a few things in terms of how to train as well the user. And what do you think? So looking at the potentially step for that.
Yeah. So thanks, Christine. Thanks, Sanja. Actually, I just wanted to cover the very last point that Sanja just made, because cancer treatment mortality, and technology are not done in isolation, of course. And the idea of GDP, quality of life, what is accessible, are equally important. And as you said, Christian, I will speak next time, and things we have looked at are the levels of GDP, access to technology, and the relations between mortality and so on. Also for the Balkan countries, as you know, Sanja. So it's fundamental reasons. So I think there are so many complicated, complex factors which interact with each other, and there are many things one has to overcome. And from where I'm sitting, and I know that Sanja would definitely, absolutely agree with me, especially being at CERN and our education is one of the primary things we have to deal with, because for raising awareness, for knowing what's possible, what's needed and where to go, and you have to work from the grassroots upwards as well. Diplomacy, yes, but also the people who have the challenges have to be part of the solution. This is one of my mantras, as everybody knows. And so coming to your African physics school, Christine, as you know, I was in the very first school that was in Stellenbosch, because I absolutely am a great believer in education, training, mentorship, and really trying to bring everybody together, because otherwise we will never succeed. And, you know, Balkans and the SEEIST problem, as, you know, Sanja has had addressed very effectively. But, you know, Africa has even bigger problems. We are just talking about even conventional radiation therapy. It's a country of 1.4 billion, and they have 400 linacs. Forget about ions or protons or anything else. And so I don't know, I mean, I will talk about things next time, but just to say, I agree with also the fact that diplomacy, technology, raising the level, also educating the young generation, but so they stay behind and they don't migrate, because certainly the salaries are low in the Southeast region, but in Africa, they are absolutely low and sometimes no salaries. So if you can bring skilled people, of course, you know, they want to leave because they want to also be able to have access to technology, but access to a decent quality of living and so on. So you have to deal with many factors if you want to be able to address these challenges, you know, whether it's cancer treatment or whether it's something else. And yes, education, GDP, technology, innovation, diplomacy, we need to do all of those. And one of the things I appreciated very much, Sanja, and you did this, is that having been situated in a scientific environment, CERN, GSI, in all of these places, but then becoming a minister, saying that in that political role, you can try to move the needle through diplomacy as well. So I think we need everything, and we need education, not only of the young people, but some of our political people as well. We were fortunate with Sanja that she already had that from a scientific ground, and when she became a minister, she understood some of the challenges we had to meet. Because I've been actually part of the SEEIST project, as Sanja will say, right from the beginning when we did the very first report with Ugo, you know, so I don't know. I think I've enough said, because it's not my seminar, it's Sanja's seminar.
Yeah. No, I just want to thank you, Majid, you really nicely explained, and I want to underline a very important role of Majid from the beginning of SEEIST, and she was a strong supporter and participating in all aspects of developing the SEEIST and contributed to the success of. Thank you, Majid. Sorry, I did not know that you are connected.
No, not at all. But it's just, the thing is, you know, it's really important. Collaboration is key. And I was fortunate enough that coordinating this European network, that we could start with the European network and with, you know, knowing Ugo at CERN and particle therapy. I mean, it just, many things come together. And as you know, I'm a great believer in bringing people together and building bridges.
So that's why it's wonderful to have those capacity as well, and those type of forum where we can open to everyone, the public, to see that there is a lot of oncoming project, and then as well the possibility to have everyone finding as well a capacity to build, to contribute. And indeed, in this case of the case of the education, I would like also maybe to mention this IFAST, so the innovation for fostering, so accelerator in science and technology, with this challenge-based innovation. So, and then to recall to our audience as well that we had in February 2023, So also this presentation by the person sharing, so this part of the review of work package 2.3, who presented the way for 2 consecutive years, so applying particle accelerator for environment, and this year, this summer, so we had applying particle accelerator for healthcare. And indeed, Ugo Amaldi gave a presentation, I gave one also, and then Menji was in the committee where there was a possibility for 44 students chosen across all Europe in different kind of disciplines, so physics and engineering, but also medicine, economy, and we had earlier as well some addition where there was communication and law that were also involved. So it really takes a lot of those disciplines to bring together as well those kind of business case, and I think it's really important to recall that we need to be united also to build up this kind of breakthrough, and we could have exactly on the line as well of that. So we have Leo Linivic, who is also with us today, and who can give also a few comments. So he also gave a presentation on the physics matter. So that was also last year.
Thank you, Christine.
Voilà,
Do you listen to me?
Yes, sir. Great to hear.
First of all, I want to congratulate Sanja for her wonderful talk. As a matter of fact, I made also a transcription of this talk, but perhaps you have one. I think that the text of it could be very useful to circulate. This is the first comment, which is marginal. But what I think is very important of this talk is the fact that a collaboration of this sort may come out from a group of countries which are small countries which by themselves do not do that. And I think that this is also a model for what we are proposing in the Caribbean, where we have a slightly different situation because Mexico cannot be considered a small country. But anyway, and it is clear that the importance of applications in medicine are an extremely important point. When Sanja was giving the figures of the number of treatments for cancer, which this type of approach can produce, this should be an argument which should fit with the political world. Of course, I realized that the fact that she was a minister certainly contributed to make easier the path, but certainly I think that this experience is very important. But I would like to add one thing. It's something which came out after I gave a few weeks ago a talk for the Iranian project of a synchrotron in Iran. I am completely convinced that the existence of a number of projects of this sort in different places, Iran, Uzbekistan, the case of the African light source, our project, this would make a case for a kind of structural connection between these projects, in the sense that the discussion with the European Union and so on about this matter would take advantage if there is some kind of coordination between the many projects of light source in the south. And for this, of course, there is no need to say, I believe that FIP and on the top of FIP, APS can play a major role.
Yeah, I greatly appreciate your comment, indeed. And it means in terms of coordination. And maybe one of the things, if we can recall, because before the SEEIST, the idea was also to have a synchrotron, isn't it? And the idea of preferring as well radiotherapy instead was more driven by the fact that the SESAME was already in the region. There was the idea of this 3GV, so with the using similar, like what you had, yeah.
Christine, may I suggest you one thing? I remember some time ago, I was a member at large of the Forum International Physics Research Committee. And I remember that the idea of having some special argument for the APS general meeting could be good. And now perhaps a discussion on the light sources in the next year FIP general meeting, FIP part of the APS general meeting in Anaheim, perhaps could be of some interest. What do you think about?
I think it's a really good idea. We had with the APS March and April meeting. So now, I mean, next year it's going to be March and April all together. So 15,000 people. So we have already, so the agenda which is fixed. We had earlier for particle accelerator looking at light source, but not specifically for or in general light source. So that's a good idea, what you propose.
No, I mean, you are in the best position to promote it.
Mm-hmm. So you can come back as well. I mean, please, for the share line of the FIP, the Forum of International Physics. We need dynamic people and proactive people.
Okay, thank you.
Excellent. Very good idea. So we have indeed, you mentioned in Iran, indeed, this light source in Iran. There was, this is also an idea that has been also quite, I mean, old. And we look also, for instance, in Turkey with the TAC. So it's always like going up and down depending on the politics. So this is why, again, having this aspect of politics under control, more or less, could be a good way.
Sure. But you know, Christine, science diplomacy is for that.
Well, indeed. So this is what we have to all think and do. And I guess that in the audience, I see that a lot of the different persons can have also an active role there. So we need indeed like north-south, like it's like the global north and the global south. We need to act so that it could be possible. So thank you very much for your comment, so Leo. Do we have additional? Yes, I see, for instance, from a comment also from Junior Masobi. So in terms and looking at young students, so he has been doing a master. So do you know if they are at the different level, indeed, master level, some program in medical physics and nuclear physics that are currently available for application for students from African countries? So ICTP-wise, I guess, or elsewhere, GSI. Could an African student apply in GSI?
Why not? I mean, there is open access and I mean, open to the world, meaning there are no borders to the scientists. And I mean, there are really a website of GSI, but also on the social media, not only of GSI, but also at CERN. You have this social media, and very often they make advertisement of the position of the topic. And of course, every research infrastructure likes young people. If you look at distribution at CERN, you see the peak is at 28 and not at 50, 60. So these research infrastructures are run by young people.
Yeah, temporary maybe, but then in a dynamic way at the given instant of their life, indeed. And this is really like, I mean, breakthrough. I mean, when you have been studying and passing by. So, I mean, we know that this is where we met, I mean, years ago. And it's like changing our life, of course. And being alumni from there, so helps for the rest of your life. And looking also from maybe we have the CERN and, I mean, Science and Society Foundation, I mean, the CERN and Society Foundation, sorry, which is also playing quite a nice role also in evolving. For 10 years already, they have been so promoting. So again, globally, so that's really good to do so. And we see also, so you see across, so the different so audience, we hear, for instance, some web page that we will pass also to from Nauri, who is writing, I don't know exactly which country in Africa, I guess, but from the large scale accelerator and laser. So there are some masters that are available in La Côte. So we will put this as well in the report and in the minutes. So thank you so much for that so presentation. So if we have no more questions. We'll try to keep it a bit more compact. And we thank everyone for your availability. So we will have, so this is what, maybe with Luisa. So if you want to have, before I give the last presentation for next month. So thanks a lot for being with us and for having enabled, so the Physics Matter series, a great opportunity for everyone to communicate and to speak with minister, with Nobels, with every aspect. So I will then now just share the my last slide, just showing next month that we will have the opportunity to welcome Menji Drossen, who will present how we can transform as well, transforming cancer treatment in low resource settings. So all those low and medium income countries, how can we handle that? What are the different statistics? And indeed, we'll hear much more from Menji then. So, and we, in the meantime, thanks everyone for attending, and please send your comment if you want for this Physics Matter. You have a QR code where you can also become a member of the FIP, or also to see what are the different advantages of becoming an APS. And again, for the lower and medium income country, there are a lot of advantage, and it's all listed on our webpage. So we thank you once again.
And from my side, I want once again to thank you very much for this opportunity. And I need to say that I really very much enjoy this discussion. Thanks a lot.
Yeah, that's the key. So thank you so much, Sanja, for this discussion and for everyone to listen. So thank you, and looking forward to seeing you. The 17th of September, potentially for the 70th anniversary at CERN, for maybe as well the other member in the audience, and soon, hopefully not being treated with this cancer, but being some of our member, so in our different organization. So thank you, everyone. Let's stay tuned and see you soon.